Hi, my name is Greg Mead. I'm a faculty member at Santa Fe College in Gainesville, Florida. This is going to be the first of a number of videos that I'm putting together for YouTube, the purpose of which in general is to help students understand the principles of geologic dating, and more specifically for my own students in ESC 1000 and GOI 2010 to help them out in the homework assignments that they're going to have, and ultimately for the exam questions that they're going to have to do as well. This is a web page that's available to the general public. If you can't read that, I'll put it in the information below the video so you can get it that way. I'm going to click on this and we will look at some specific issues. Click on class lecture schedule and then go to geologic time. And the first part of geologic time that we're going to address is relative geologic dating, and that's what the subject of this video is. So let me scroll down to the area that we're going to be looking at, and these are all things that you can look at on your own, which will help you understand the principles that we're going to be talking about. But I'm specifically today going to show you how to apply these principles with relatively realistic geologic cross sections. And in here there are, as you can see, 13 different geologic cross sections which you can do on your own. The answers are given to most of them, not to the ones that I'm going to actually have in the exercise. I will show you how to figure out the relative age for 3 of these, beginning with a very simple example and then going up to more complex examples. So the first one we're going to look at is cross section number 4. And this is a fairly simple one. Many times students will look at something like this and they will be terrified because it looks very, very complex. But if you take this as a series of steps and use the methodology that I'm going to show you right now, you'll find that they're fairly easy. So the first thing to do when you're doing a problem like this is to recognize that we have sedimentary layers here and here and here. We have, in this case, one igneous intrusion, and I apologize. I did this 20 years ago and I've never cleaned it up. We have a couple of unconformities and we have a fault, and then, as I said, we have the sedimentary layers. So the first thing to do when you're approaching a problem like this is to put the sedimentary layers into proper geologic order. And when you do this, the standard way of doing this is to make a list with the oldest layers on the bottom. And so the oldest layer, because of the principle of superposition, and you can look that up in the web page that I showed you that I got to from here, the oldest layer is layer I. And then we can go layer I, J, K, L, M, and N, and then the next layers are H, G, and E. And then above that, we have D, which is actually part of this sequence, then B and A. And so you can see that even though this looks very complex, by doing this, we've done most of the work already. We've probably done 80% of the work. So the first step is always to put the sedimentary layers into order. The second step is always to look at the unconformities. And we have 2 unconformities. We've got P and C. So let's look at P. You can see P erodes over layers I, J, K, all the way up to N. And so by the principle of cross-cutting relationships, this tells us that P must be younger than the layers that it erodes through, that it cuts through. So we can put P right here, telling us that it's going to fit in right there. Now the next question is, how old is P relative to H? H has been deposited on top of P. So by the principle of superposition, H must be younger than P. And so we can actually say not only is P younger than N, H is younger than P, or P is older than N, H, the same thing. When we look at layer C, or unconformity C, we see that C has eroded through D and eventually F, which we'll get to. But D has been eroded by C. So again, by the principle of cross-cutting relationships, C must be younger than D. So here's D, and so we can put C right there. We can see that B has been deposited on top of C. And because it's been deposited on top, that means that B, by the principle of superposition, must be younger than C. So it goes right there like that. Now the next thing that we have to deal with are the fault and the intrusion. And it doesn't really matter which one of those you do first, because O, the fault, which cuts through all these layers, is so obvious. Let's do that one next. And so we can see that O offsets everything here all the way up to the surface and cuts through all those different features. And because it cuts through, the principle of cross-cutting relationships tells us that O must be younger than everything here, including A, which is the youngest feature up till now. So that tells us that O has to be right there. Finally, we see that F is an intrusion. Intrusions are always cross-cutting features. Everything that they cut through must be older than the intrusion, or another way of saying that is that the intrusion is younger than everything that it cuts through by, again, the principle of cross-cutting relationships. And so you can see F cuts through all of these features. It cuts through L and M and N and the unconformity and H and G and E and D, but it doesn't cut through C. And the reason for that is that C erodes through it. The fact that there's an erosional surface here rather than F going up here tells us that C cut through the already existing F. And therefore, F must be younger than all these features, but C is younger than F. And so that tells us that F belongs underneath C and above D, like that. And now we've looked at every single feature here. And because of that, we can now take all of these and we can clean this up. Whenever you do these, always do them in something that's erasable. This is a pen, but usually you're going to do this with a piece of paper and a pencil. And that way, if you make mistakes, you can fix it. And once you've got this into the correct order, then we can go and put all these in a nice, neat column. O, A, B, C, F, D, E, G, H, P, N, M, L, K, J, and I. And if you click on want to see the solution, that will give you this same order, and it's kind of messy because it's superimposed, but you can see all of these different features are present in the same order. Now the one thing we have not addressed is the fact that these layers are tilted. And the principle of original horizontality tells us that sedimentary layers are originally horizontal, and that means that if we find them now tilted, the tilting occurred after they were deposited. And so if this question asked you, when did the tilting occur, you would say the tilting occurred, because erosion is usually relatively horizontal, the tilting occurred after N was deposited and before it was eroded. And so the tilting would be right at that point. So this is a fairly simple one, and it took us, what, maybe 5 minutes? I think that's not too bad. So let me erase these and go on to a slightly more complex example, and in some ways a little bit trickier example, and this is going to be number 6. Oops, not number 6, sorry. Let's see, which was it? There it is, number 7. That's the one that I wanted you to look at. Okay, so number 7, and let me look at the camera and make sure that it's recording it properly. Yeah, that's pretty good. Number 7, we again have a bunch of different sedimentary layers. We have 2 faults, one fault here, another fault here, which has been separated by this fault. And we've got 2 igneous intrusions, this one down here and this one here. And lastly, we have another unconformity, which is right there. So let's take a look at these and do this in exactly the same way that we did the other problem. We are going to start by putting all the sedimentary layers into order. So the first layer, the oldest layer, is the one typically on the bottom. And so that is O, then N, M, L, K. You can see alphabetically, this is in reverse alphabetical order. And so we have O, N, M, L, and I'm going to do that as a script L to make sure that you know it's not a 1. Then K, then J, then I, then H. And that's of the tilted sequence, that's the one on top, so it's the youngest by the principle of superposition. And then we can go G, F, and E. And there's a layer here that's not labeled, but obviously it's between those two. So G, then F, then E. Again, the next thing you're going to do is to do the, in this case there's only one unconformity, so we'll do one unconformity P. P, by the principle of cross-cutting relationships, is younger than anything that it erodes through, and so it's younger than all these sedimentary layers, so it's younger than H. And we can put P right there. Then we can notice that G has been deposited on top of P. So G, by the principle of superposition, must be younger than P. And so that puts P neatly right there. Again, you can do these in any order, the faults and the igneous intrusions. And let's do the faults, just for the sake of argument, let's do the fault first. And notice that D cuts through all these layers all the way up to the surface. So D is the youngest layer, or excuse me, D is the youngest feature, it's not a layer, relative to E, so D has to go up here. What about A, which is this fault right here? Well, notice that A is offset. Well, first of all, A cuts through all these layers, and it's a little ambiguous. We can assume that A cuts through H, but it's been eroded away. So A must be younger than H, but A has been truncated by P, which means that P came along after A formed and eroded through it. So A is younger than, we're going to assume H. A is younger than H, but older than P. So A has to go down right here, in between H and P. Now, when we look at these other features, we see something kind of interesting. We see B, an igneous intrusion, has come up through these various layers. Now, we can see that B has cut through or melted through or cracked through all the sedimentary layers up through M, but notice also B truncates D. This fault rather used to extend farther down, but then it was melted away by B. So B actually has to be younger than D. So B goes here. Then notice C has melted its way through B, and B is the youngest so far. So C actually has to be younger than B. So this, surprisingly, even though these are down, not making it all the way to the surface, these two intrusions are actually the youngest features here. So again, once we have all of this into proper order like this, we can go C, B, D, E, F, G, then P, then A, then H, I, J, K, L, M, N, and O. So that's the order that we would put this in. And this would be what you would put down for your final answer. Again, all the sedimentary layers are in proper order due to the fact that we have the principle of superposition that tells us that the oldest layers are on the bottom and younger layers get deposited on top of that. We could also look at the tilting and notice that the tilting has tilted all these sedimentary layers, but then this layer, approximately horizontal, must be younger than the tilting, so the tilting would have to be younger than sedimentary layer H and older than P. So the tilting would go, well, we can't actually tell how old it is relative to the fault, but that means that the tilting would go somewhere around here. Okay? So again, it's the same process that we used for each of these. Okay. Well, we had a little bit of a malfunction last time, and I didn't get a chance to show you the last cross-section, so we're going to do that right now. So what we're going to do is, after you've seen the processes and methodology behind figuring out geologic cross-sections, and so we're going to do cross-section number 13, excuse me, which is a more complex cross-section. And I think you'll find that even though this is a more complex cross-section, you'll find that it's no more difficult to do, that the same methods are used in this one as we had in the last couple of cross-sections. So again, when we look at this, we can see that there are two AA, B, and BB, two igneous intrusions. There are now three, this one, and this one, three unconformities, and there are a number of different types. This one is a disconformity because the layers below it are parallel to the unconformity. This is a angular unconformity because the layers below the unconformity are at an angle to the unconformity. And this is also an angular unconformity because the layers below it are at an angle. I want to point out to you that wherever the intrusion runs into the unconformity, at that point it's known as a nonconformity because intrusions, igneous bodies as well as metamorphic bodies, are unbedded. And so you can't talk about whether a bed is parallel or at an angle to an unconformity if you don't have sedimentary rocks. So we call those nonconformities. So we have igneous intrusions, we have unconformities, we have two faults cutting through this area, and everything else is a sedimentary layer. And so, just as we did last time, we are going to look at the sedimentary layers first. And if you look at the sedimentary layers from the top down, you'll see you get lower and lower and lower, and I is the lowest sedimentary bed. So from bottom to top, we have I, J, K, L, M, N, O, then A, B, C through F, and F is a big thick body. So A, B, C, D, E, F. And then finally S, T, and U, and then R, Q, and P. And I'm going to actually redraw this so that we can get it all in there. So I, J, K, L, M, N, O, A, B, C, D, E, F, S, T, U, and then R, Q, P. And again, notice that while this looks extremely complex, we've just done 80% of the work just by getting the sedimentary layers in there and without looking at the things that make this more complex. So the next thing we do, just like we did in the last two examples, is we look at the unconformities. And this is probably the easiest one, so let's do that Z first. Z cuts through, erodes through U. So by the principle of cross-cutting relations, Z has to be younger than U. So we put Z right here. Now how old is Z relative to these? Well, notice that R is deposited on top of Z. So R must be younger by the principle of superposition. So we can put Z right in between U and R, which I think is fairly obvious. The next thing we can look at is Y, this unconformity. And even though Y is offset by this fault, we can see that Y cuts through or erodes A, well, we don't quite get A, but A would be out here. A through E, and even F is eroded by Y. So Y must be, by the principle of cross-cutting relations, younger than F. So here's F. Y is younger than F. And then S is deposited on top of Y. So S must be younger than Y, and so Y fits in very neatly right there. Our last unconformity, X, you notice is an angular unconformity. It erodes all of these features from I through J, K, L, M, N, O, all the way through O, and if there were other layers up here, it would probably erode through that. So X must be younger than O, right there, and A has been deposited on top of X, so by the principle of superposition, A must be younger than X, and so we have our three unconformities finished. The next thing that we can do, and this has been true for the other exercises, we can do either the intrusions or we can do the faults. And I'm going to adjust this slightly so that we can see this a little bit better. There we go. And take your pick. Let's do the intrusions. A is down here, and notice A, because it's an intrusion, it cuts through previously existing rocks, and so it must be younger than anything that it cuts through. And notice that it cuts through I, J, K, L, and there's this little dike that comes up. So AA cuts all the way through O, and so it must be younger than O. But notice that X has eroded AA, and so that tells us that AA must be younger than all these, and X must be younger than AA, so AA sits right there. When we look at BB, BB cuts through A, among other things. It's younger than A, but it's also younger than all these features, all these features. It cuts through S and T, and there's a little bit of U right here. And so it cuts through U, but it in turn is cut by Z. It's eroded by Z. And so BB has to be younger than U, but older than Z. And so BB fits in right there. The last features that we can look at are the faults. And let's look at fault V first. Fault V, notice it cuts through AA, it cuts through K and L, it cuts through the unconformity X, it cuts through all of these sedimentary layers, including F. And so V must be younger than F through the principle of cross-cutting relations. But then Y, this used to extend up farther than that, but Y has since eroded away not only all the layers above F, but the fault V that cut through it. So V must be younger than F, but Y must be younger than V. So V has to fit in underneath Y and above F. Our last fault, and the last feature, in fact, that we're going to look at, is W. And notice W cuts through all these things here and cuts all the way up through U, but is itself truncated or cut by Z. So we know that W has to be younger than U, but older than Z. But how old is W compared to BB? Well, notice BB is not offset by W, but in fact BB cuts through or melted through or cracked through W. So BB must be younger than W. W is younger than anything that it cuts. So W is younger than U, but older than BB, or BB is younger than W. So here's BB, and W is younger than BB, older than BB, and younger than U, so W goes right there. And the net result of all of this is that now that we have all these different features in proper order, we can start at the bottom, I, J, K, L, M, N, O, and then AA, then X, then A, B, C, D, E, F, then V, then Y, then S, T, U, then W, then BB, and we're going to run into this lettering up here, but I hope everybody can understand it. Then Z, R, Q, and P. And we have finished this cross-section by using exactly the same processes and exactly the same principles, rather, of relative dating that we used for the other simpler cross-sections. And if you want to make sure that you got it right, as you're working through these, click on Want to See a Solution down here, and it will show you. And I don't know if you can see it in the video, but I, J, K, L, M, N, O. then AA, then X, then A through F, then V, then Y, then STU, then W, then BB, then Z, and then RQ and P. So we have successfully figured out how to use the principles of relative dating, mostly the principles of superposition and cross-cutting relationships. But if we want to, for instance, figure out when tilting episodes have occurred, we know that this tilting must have occurred before the formation of this unconformity, because unconformities are generally horizontal, or at least close to horizontal. This tilting episode must have occurred before the formation of that unconformity for the same reason. And so we can figure out when the tilting has occurred. The last thing I want to do, you'll notice, I hope, that all of these hand-drawn or computer-drawn cross-sections that I've shown you have had sedimentary layers, igneous intrusions, faults, and unconformities. And it would be a little bit unusual to find a feature with all of those different features, a geologic feature or a geologic cross-section with all of those features in one place. But we do find things that are similar to that. And I want to show you a feature that I saw when I was, this is back in the 1980s, I was driving around in Utah. I was actually visiting, I was on vacation visiting some national parks. And when you look at this, you can see that 3 of the 4 different kinds of features that we talked about before are present. We have a number of faults. Here's a fault there. There's a fault there, a fault there. These are all faults that are offsetting these rocks. And we haven't talked about types of faults, but those are known as normal faults. We have an angular unconformity right here. We have a series, and I'll put it in a different color. We have a series, oh, and I think there's a fault right here as well. Looks like there's some offset of layers. And we have layers that are tilted like this. So that makes this an angular unconformity. And then we have a series of layers here. It's covered more with sediment that's eroding off, but we have some other sediments here as well. And so when we look at this, we can say that by the principle of superposition, this is the oldest layer. They get younger as we go up through the section here, and then we get more layers here. And so this is the youngest layer. This is a limestone layer, which probably represents an ancient reef. I'm not sure what these others are. I don't know if you can see there's a fence here, and out west you don't cross fences without permission because they can shoot at you. So I just took this photo from the road. But we've got this sequence of sedimentary layers. Then these faults cut through the sedimentary layers afterwards by the principle of cross-cutting relations. And then this, which if I was making this as a formal drawing of a geologic cross-section, I would show it with a squiggly line, which is the standard geologic signal for an unconformity. And so then we have our angular unconformity, which is younger than the faults because it cuts through the faults. And then we have sedimentary layers on top. And so this would be the youngest feature. This would be the oldest feature. The faults would be younger than these sediments. The unconformity would be younger than the faults. And then all these sediments would get younger as you worked its way up towards the surface. So this is not, the things that we've learned in this video are not unrealistic. We really do see features like this in the real world. And if you're ever lucky enough to drive between Zion National Park and Bryce Canyon National Park in Utah, this is right along the main road that goes there, and you'll be able to see it. This is a well-known enough feature that years after I took this photo, I found a photo of this in a textbook, not my photo, but somebody else passed this same feature and decided that it was a good enough feature to be shown in chapters on structural geology and in chapters on geologic time. So I hope you've enjoyed seeing these different cross sections. There are, as I said before, excuse me, a number of practice cross sections, so that if you want to try doing some of these on your own, they not only have the cross sections themselves, but they have the answers either here or within the web page on the cross section, and so you can work on these yourself. And I hope you find them fun. I find them to be puzzles, real world examples of puzzles that we can also make drawings of. Okay, I hope you enjoyed this.